Hi students, this is Viswanath, chemistry faculty for NEET and IIT exams. In last class, we completed photoelectric effect. Now see the related numericals. The threshold frequency nu naught for a metal is 7.0 into 10 power 14 second inverse. Calculate the kinetic energy of electron emitted when radiation of frequency nu equal to 1.0 into 10 power 15 second inverse hits the metal. Here see this is threshold frequency 10 power 7 into 10 power 14 second inverse. This is incident beam frequency 1.0 into 10 power 15 second inverse. Generally students may get confusion. Here 7 into 10 power 14, here 1 into 10 power 15. So 7 is bigger than 1. That's why threshold frequency is more than frequency of incident beam. So electrons cannot be ejected from the metal, but that is wrong. See carefully. 7 into 10 power 14 exponential part compare 10 power 14 10 power 15, which is bigger? This one is bigger. So incident beam frequency is more than threshold frequency. That's why electrons can be ejected in this case. Now see the threshold frequency calculation. Already we know that according to Einstein's equation, kinetic energy is equal half mv square, that equal to h into nu minus nu naught. Nu means incident ray frequency, nu naught threshold frequency. So h means Planck's constant, we know that. Substitute that value, that is this one. So this, now we have to subtract these terms. When we are doing subtraction for this type of numbers, in first chapter we completed subtraction, addition, multiplication and division of these type of exponential terms. First we should change these exponential part to the same value. Here 10 power 15, 10 power 14, we should not subtract as it is. Convert this 10 power 15 or convert this 10 power 14. Both should be having same exponential value. So for that purpose, I converted this 10 power 15 into 10 power 14. Then we can get 10. So 10.0 into 10 power 14 minus 7.0 into 10 power 14. Now 10 power 14 by taking as common we can get this one. Now do the subtraction. Then finally we can get. So be careful while you are subtracting or adding these type of numbers having exponential parts. Okay, for this kinetic energy is this one. Okay, next see the next one. Threshold frequency of a metal is f naught when light of frequency nu equal to 2f naught is incident on the metal plate. Velocity of electron emitted is v1. When the plate is exposed to frequency of incident radiation is 5f naught. v2 is the velocity of emitted electron. Then v1 is to v2 is a metal having threshold frequency f naught. Here two cases are there. In the first case, incident ray frequency 2f naught, then ejected photoelectron velocity v1. Second case, incident ray frequency 5f naught, ejected photoelectron velocity v2. Now we want ratio of v1 and v2. So for this, see this. Threshold frequency for a metal f naught, frequency of incident light first one 2f naught, velocity v1. So from Einstein equation we can get this relation. So now nu means frequency of incident light 2f naught, nu naught threshold frequency f naught and velocity v1 square. So from this we can get this one. Second case, incident light frequency 5f naught, velocity v2. So substitute in the Einstein's equation, then we can get this one. Now ratio 1 by v1 by v2. So that's why we are doing like this. So finally we can get this one. v1 is to v2 equal to 1 is to 2. Okay. So what is the option? Option B is the answer. Now see this one. Next question. The kinetic energy of electrons ejected by using light having frequency equal to threshold frequency nu naught is, suppose incident light frequency is exactly equal to the threshold frequency, then what about kinetic energy of the photoelectrons? Almost zero, because threshold frequency and incident ray frequency is the same. Same means all the energy of incident ray is utilized to overcome the attractive force of the nucleus. That's why the emitted electron and kinetic energy almost zero. No kinetic energy. So option B is the answer. Okay. Next. See this next question. Next one. In photoelectric effect, the number of photoelectrons emitted is proportional to. Yesterday we completed this point. In the last class we completed this point. In photoelectric effect, the number of photoelectrons emitted is proportional to intensity of the incident light. Here number of electrons means it depends on intensity of the incident light. Incident intensity is more number of photoelectrons. Intensity is less number of photoelectrons. So option A is the answer. Next, say this next important topic in this chapter, spectrum. What is meant by spectrum? The systematic arrangement of various wavelengths of light is called spectrum. In nature also, in rainy season we can observe spectrum, that is rainbow. Rainbow having VIBGYOR, violet, indigo, blue, green, yellow, orange, red. So that is also spectrum, because all these colors, 7 colors having different wavelengths, and all those are arranged side by side. So that is also spectrum. This spectrum broadly classified into 2 types, continuous, discontinuous. Again, discontinuous is subdivided into emission, absorption. Now see the continuous. If various wavelengths are arranged continuously without any gap, then it is called continuous spectrum. Simple example, VIBGYOR formation. That means rainbow. VIBGYOR formation, if we observe, we can understand all the colors, violet followed by indigo, followed by blue, followed by green and yellow and orange and red. So between these 7 colors there is no gap. Side by side all these colors are arranged. Such type of spectrum is called continuous spectrum. Same thing. When a white light is passed through a prism and take the spectrum of it is called continuous spectrum. Simple example, VIBGYOR formation. Next, discontinuous spectrum, emission spectrum. The light emitted by an excited sample can be passed through a prism and separated into different wavelengths is called emission spectrum. Take a light. If a substance absorbs light, then the atoms present in that substance go to the excited state and then come back to the ground state. When these excited atoms come back to the ground state, they emit radiation. For that, if we take spectrum, that is called emission spectrum. The light emitted by a excited sample can be passed through a prism and separated into different wavelengths is called emission spectrum. If we pass a light to a substance, then the electrons in that atoms absorb that energy and go to the higher energy level. But in that higher energy level, they cannot stay for a long time. Immediately, in a fraction of seconds, they come back to the ground state by emitting radiation. For that emitted radiation, if we take spectrum, that is emission spectrum. I hope you understand this one. Next, in this, bright lines appeared on the dark background, so it is also called line spectrum. In this emission spectrum, we can observe bright lines on the dark background, so it is also called line spectrum. Next, this emission spectrum is also known as atomic spectrum, because generally atoms exhibit this type of emission spectrum. When light rays fall on the surface of the particular substance, then atoms absorb that energy and go to the excited state. In that atoms, electrons go to the excited state and come back to the ground state. So atoms exhibit this emission spectrum. That's why it is also called atomic spectrum. Next, absorption spectrum. When a white light is passed through a sample of substance and the transmitted light is recorded on photographic plate, then that spectrum is called absorption spectrum. Say this, absorption spectrum. When white light is passed through a particular sample of the substance and some of the wavelengths are absorbed by the substance and remaining wavelengths are transmitted. For that transmitted light, if we take spectrum, that is absorption spectrum. Suppose 10 wavelengths are there in that light. From that 10 wavelengths, 3 wavelengths are absorbed by the sample of the substance. Remaining 7 wavelengths are transmitted. For these 7 wavelengths, if we take spectrum, that is absorption spectrum. In this, dark lines are present on the bright background. Here, 3 wavelengths are absorbed by the sample of the substance. At these places, dark lines we can observe in the spectrum of the transmitted line. That is nothing but absorption spectrum. Total 10 wavelengths, 3 absorbed by the sample of the substance, 7 wavelengths are transmitted. In the absorption spectrum of those 7 wavelengths of transmitted light, we can observe dark lines at 3 places. Those are related to those absorbed wavelengths. So in this, dark lines are present on the bright background. So it is also a line spectrum and is a photographic negative of emission spectrum. See here, 3 wavelengths are absorbed by the substance. Remaining 7 wavelengths are transmitted. For that transmitted light, if we take spectrum, that is absorption spectrum. In that absorption spectrum, at these 3 places, dark lines are appeared. For those 3 wavelengths, if we take spectrum, that is emission spectrum. That means by absorbing that 3 wavelengths, atoms of the substance go to the excited state. That is, electrons absorb that energy, go to the excited state and then come back to the ground state by emitting radiation. For those 3 wavelengths, if we take spectrum, that is emission spectrum. So this absorption spectrum we can consider as photographic negative. At which wavelength radiation is absorbed by the substance, at the same places we can get dark lines in absorption spectrum. So it is a photographic negative of emission spectrum. I hope you are cleared about emission spectrum and absorption spectrum. Next, line emission spectrum of hydrogen. Say this, each element has a unique line emission spectrum. The characteristic lines in atomic spectra can be used to identify unknown atoms. Every element having line emission spectrum, but no 2 elements do not have same type of line emission spectrum. Each one having unique line emission spectrum. Based on this line emission spectrum, we can identify any unknown elements. Any new elements were discovered in the nature. For those unknown elements, if we take line emission spectrum and comparing the lines of that unknown element with the known element line emission spectrum, if exact match occurs, then we can say that particular unknown compound having this known element. Otherwise, the unknown substance having new element. Okay. Next, when H2 gas is irradiated, that means electric charge is passed through the H2 gas, then hydrogen atoms are produced. Those hydrogen atoms emit radiation of discrete frequencies. That means different frequencies. The hydrogen spectrum contains a number of group of lines. Balmer observed a series of lines in visible region is called Balmer series. If we see hydrogen spectrum, different spectral lines are observed in different groups. Each group was identified by a particular scientist. So those spectral lines are named after the scientists who discovered them. So Balmer discovered a spectral lines which are appeared in the visible region. Those are called Balmer series. Say this, the wavelength or wave number of all series of lines in the hydrogen spectrum can be expressed by an equation called Rydberg equation. That is, nu bar, wave number nu bar equal to 1 by lambda equal to RH into 1 by n1 square minus 1 by n2 square. Where RH equal to Rydberg's constant for hydrogen atom, value 1,09,677 centimeter inverse. Here N1 equal to lower energy level, N2 equal to higher energy level. A Rydberg constant value is not same for all the elements. It differs from element to element. For hydrogen-like species, example He plus, Li2 plus, Be3 plus, Rydberg equation nu bar equal to 1 by lambda equal to RH into Z square into 1 by N1 square minus 1 by N2 square. Okay, we will meet in the next class.